So the first thing we are going to put down in this box at the top, y sub 0 represents the amount present at time 0. So it's your beginning amount. And then under certain conditions, the amount present at any time is given by this equation. Y being the amount we have, y sub 0 being the amount we began with, e to the kt. K just represents a constant in this. If your k is greater than 0, that's exponential growth. If your k is less than 0, that's exponential decay. So let's look at our first example. Exponential functions are actually used a lot to model population growth. So that's one situation. This one is looking at carbon dioxide levels. So we are given some information and we want to find a function that gives the amount of carbon dioxide in a given year t. So we are talking about this formula, our exponential growth. Y sub 0 is our beginning amount. How much should we begin with? 353 is when this table starts. Okay. Let's add something to this. I'm going to add a t. Because if I'm starting this thing when the table begins, 1990 would be like when t is 0. So in 2000, t would be 10. 2075, t is 85 because we started in 1990. 2175, and 2275. Okay. I already know my y sub 0. What I have to find, we have to know the two pieces, the k and the y sub 0. So what we're going to do to find out our k is plug one of these points in. It doesn't matter which, I'm just going to go with the final one. So what is our y value there? 2000. Our beginning amount, our y sub 0, was 353. E, the k, we don't know. T, what was my t there? 280. Okay, so if I'm going to solve this, what would I do first? Okay, if I divide my 353, that gives me a decimal. I don't really want to round this too much because every time you round, it's going to throw your answer off a little bit more. So I'm just going to leave this as a fraction for now. Okay, so if I'm trying to find k, what would I do now? How do we solve these exponentials when you need to get the exponent? We put an ln on each side. The benefit of that is the exponent comes down. What is it, ln of e? 1. So you could choose to drop this if you didn't recognize that. Just divide it over, you'll get the same answer. So then to get my k by itself, I have to divide by my 285. So that's what I'm going to put in my calculator. Natural log, parentheses, 2000 over 353. Close my parentheses, all divided by 285. I didn't specify how many decimal places, so I'm just going to write it like this. So our equation is y equals y sub 0 is 353, e k is 0.006086 t. So now for any year, we could estimate our carbon dioxide level. Any other questions? Part B says, estimate the year when the future levels of carbon dioxide will double the 1951 level of 280 parts per million. So if we double it, what level do we want to reach? Okay, come on guys. You double 280. Thank you. So that has to be our y. If I plug that in for my y, so 560 equals 353 e kt. What do we do first? I'm just going to leave this as a fraction for now. And then what do? Add our natural log. All we're really doing is solving these equations like we did for our test. We just have word problems to go along with them. So the exponent comes down. ln of e. We know the ln of e is 1, so you could choose to drop that. So you just have to divide by your So 75.2, is that what you guys got? Now, that is my t value. So if I wanted the actual year, if this thing started in 1990, we're during the 75th year, so 75 years after 1990. So if you add 1990 to that, what are you going to get? The 0.8 is really irrelevant. It just tells you later on in the year, but it's still during the year 2065. If you looked at your tables, we were estimating when it would hit 560, which is in between those two levels, and 2065 does fall in that range. So we can be pretty confident that this is correct. Questions about that? I'm going to skip around on here a bit. I think I'm going to skip example 2 or example 1b for now. We may come back to it later if we have time. Okay, we've done problems like this before. We set them up anyway. We were solving for different things. I think we used to solve for the interest rate. Now it's asking you to solve for the time. But we've done this thing before. How long will it take for the money in an account that is compounded continuously at 5.75% to double? So remember, your compound interest formula is A equals P E to the RT. I haven't given you a ton of information. What's the 5.75? The rate. How would I put that in? 0.0575. I just said I want to double my amount. So You could keep A and P as variables. Let's just make up a number. What do you want to use for your P? 100. So what would your A be? 200 if you want to double it. Okay, so if we plug this in, alright, you guys solve that equation. So to get the E by itself, you have to first divide by the 100 because it's multiplied. Then what should you do? Add our natural log. With that, the exponent comes down. If you choose, you could drop your natural log of E because it is a log base E. Those cancel. So I have a natural log of 2 divided by 0.0575. So it takes approximately 12.05 years to double. Any questions on that one? Like I said, we have done those before, so that one really isn't new. Do I need to do another one? Let's go to example 3. Something looks a little different anyway. Okay, according to the U.S. Census Bureau, the world population reached 6 billion people on July 18, 1999 and was growing exponentially. By the end of 2000, the population had grown to 6.079 billion. The projected world population in billions of people, T years after 2000, is given by this equation. So really, that's the important part here. They gave you some of the background on how they developed that equation, what numbers they were using, but the important piece here, that's our function. T is the time after 2000, and the F of T represents the population. What will be the world population at the end of 2015? Okay, so, am I plugging in 2015 in for T? Right. T is the years after 2000, so that would be 15 years. So if I plug that in, get 7.3437. What would that be? What would my label be? Part B. In what year will the world population reach 8 billion? So what do I do there? Right, the 8 is your F of T. We have to divide. I don't really want to round, so I'm going to leave that as a fraction right now. What would you do next? Add our natural logs. And the exponent comes down. Yes?
Why did you put 7.3437?
I don't know. It should be 6.079, shouldn't it? Okay. Yeah, I don't really know why I did that. So, you're setting the population equation, which was 6.079 e to that power equal to 8. So then we're going to divide. And add your logs. Okay, is that less confusing? We know the natural log of e is 1, so we could drop that. Then we divide by the 0.0126. So you guys get for your answer 21.79. So this is years since 2000. So what year is it going to happen? During 2021, based off of this model. You're welcome. Any other questions? Another one. Have you guys ever talked about like half-lives of substance or anything like that? This is an exponential equation, so it can be solved similarly. So if 800 grams of a radioactive substance are present initially, and 2.5 years later, only 400 grams remain, how much of the substance will be present after 4 years? I didn't give you the equation, so we are assuming just our regular exponential growth or decay function. So our y equals y60 e to the kt. Would this one be growth or decay, do you think? Decay, because we had less of it as time goes on. Okay, what is our y sub 0? How much do we have to start with? 800. We have to find k. So to do that, I know after 2.5 years I have 400 grams. So what would I plug in for my y? 400. My beginning amount was 800. E, I don't know k. And my t is 2.5. Divide by 800. You get 1/2. This is what's called a half-life. Just the time until you have half of what you started with. And then what do we do? Add your natural log. We know the natural log of e will cancel, so we can drop that. Next one it comes down, so divide by our 2.5. Get my k, it's negative because it's decay. I'm going to keep a lot of decimal places. On the exponentials, your exponent has a huge impact, so if you round it only to a few decimal places, it will throw off your answer quite a bit. Now, all I've done so far is essentially figured out what my equation is. My equation is actually y equals 800 e to the negative 0.277259 t. What was the question we were asked? How much would be present after 4 years? So now what do you think we have to do? Plug a 4 in for t. So we had to first figure out the equation. Then we can plug in our 4. So I get 263.9014. What are we measuring in on this? That was grams for me. Alright, any questions there? Why don't you guys do the work? You're going to plug in the 300 after 3 years. So you divide, add your ln, divide by 3, and so you get your k to be a negative 0.231049. So your equation is y equals 600 e to negative 0.231049 t. Then we want to know how much is present after 6 years. We plug that in. What do you get? 0, 0, 0. So 150 grams remain after 6 years. All right. How was that one? Good? Okay. I want to do at least example 5. If we get to 6, that's great. But I just want to get at least one more. This one is pretty similar, but slightly different. The amount of radiocarbon, carbon-14, present after T years is given by this equation, where Y sub 0 is the amount present in living plants and animals. This is what's called carbon dating. You know, when they find remains, they can determine the age from this process. So I want to find the half-life. Now this one is different. I already gave you the K value. So unlike previous problems, we're not finding that. But I also didn't even tell you what your Y sub 0 is. So any ideas on how we could find the half-life? What is a half-life? Okay, we could make up a number and plug it in. Is that what you guys want to do? There's really 2 approaches we can make. We can keep it in terms of variables, or we can make up a number. If we make up a number, so let's say, what do you want to use for your Y sub 0? 10? Then the half-life means the time until you have half remaining. So what would we use for our Y? 5. And we are trying to solve for T here. So you divide by 10. Then what? Add our natural log. We know the natural log of E is 1, so that drops and your exponent will come down. So we can just divide. And what did you get? .2235 years until you have half of what you started with. Okay. Part B. Charcoal from an ancient fire pit on Java contained 1/4 of the carbon-14 of a living sample the same size. Maybe age of the charcoal. What do you want to do here?
On the last one, couldn't we just, do you want us to make up numbers, or couldn't we just put 1/2 and then not put the Y's in there?
Yeah. So if we did this one without making up numbers, for instance, if Y sub 0 is the amount you start with, what was the formula? Then if I want to end with 1/4 of it, you would basically end with 1/4 of what you started with, 1/4 times Y sub 0. And when you divide by the Y sub 0s, those are going to keep. So if you just set it equal to 1/4 without the Y sub 0, that would be fine too. So then we can add our natural log. And you guys are all okay that I'm not writing my natural log of E over here anymore. You know why I'm dropping that. So how old is this charcoal? 1,400 charcoal. Any questions there? Let's do 6A. That's going to be my last one. Oh, let me go ahead and do it. Newton's law of cooling says the rate at which a body cools is proportional to the difference C in temperature between the body and the environment around it. The temperature F of T of a body at time T in appropriate units after being introduced into an environment having constant temperature T sub 0 is this. Okay, lots of stuff here. T sub 0 is the constant temperature of the environment, so if I stuff something in this room and this room is 70 degrees, that's my T sub 0. C and K just represent constant values. A pot of coffee with a temperature of 100 degrees Celsius is set down in a room with a temperature of 20 degrees Celsius. The coffee cools to 60 degrees Celsius after 1 hour. Write an equation to model the data. So T sub 0, that is the constant temperature. What is that? 20 degrees Celsius. That's the temperature of the room. Okay. It tells us, we know C is a constant. C is the difference in temperature between the body and the environment around it. So C is, difference means you subtract the body and the environment. So it would be like my coffee minus the room. So my C in this problem is going to be 80. Now K is a constant, but it doesn't tell us what that is, so we're going to have to use this to plug in and find it. Okay. Does it tell us up here if T just says T is in appropriate units? So we can do it in terms of hours, or it might be more useful to do it in terms of minutes. It doesn't really matter. You just have to let me know which one you're setting up your equation as. We will get a different constant value if we're doing it in minutes versus hours. But like on part B, if I write my equation in terms of hours, I'd have to plug in 1/2. Or if I did it in terms of minutes, I'd have to plug in 30. So you have to know what your units are. Do you guys want to do this in hours or minutes? Minutes? Okay. So we're going to plug in, so my F of T, that was my temperature, so that would be a 60, is my T sub 0, my 20, plus my C, which is 80, e to the negative k times my my time, we decided minutes, so that would be 60. This one's a little bit different, but how do we solve this? Subtract the 60. Divide by 80. Then, just like all of the others, we add our natural log. Natural log is E drop. So our equation is F of T equals 20 plus 80 e to the negative 0.011552 t. So really we have a lot of repetition here. We're doing the same thing over and over again once we set up our initial equation. Question 6. Let's look at part B. Find the temperature after half an hour. Make sure you're with me. What are we going to plug in for our t? 30, because we made our constant in terms of minutes. So just take your equation. We're going to put this in our calculator. And so we get a temperature of 76.57 degrees Celsius. Last one, part C. How long will it take for the coffee to cool to 50? What do you do at the 50? That goes in for your F of T. So we can subtract our 20. Divide the 80 over. The natural log again, and the natural log of E drops. So we get that it has been 84.9, and remember we measured ours in terms of minutes. 84.9 minutes. Do you guys have questions? So really, the reason I wanted to go through this section is to show you some scenarios where this stuff is actually used. You know, in modeling populations, a lot of research, like scientific research, goes back to these types of equations. So, homework. This is what I had for you guys, but because this is mostly the same thing over and over again, and it's all goes back to solving those equations, and you guys did so awesome on this test, I'm so happy with that, I'm not giving you any homework. So you don't have to do this, there is no homework for tonight, and we will start the next chapter tomorrow. Okay?
Thank you.
You're welcome. So not quite the same as a free day, but Riley and Logan. Riley. Thank you. Yeah, of course. Hey, don't show him that, but that's Do you have any questions, Logan? Do you have any questions for me?
No.
Thank you.
I went back in and plugged in every single thing. Yes.